mechanical superpositions, they had just a pure academic interest. However, already in this century, at the end of the 20th century, the situation dramatically changed because new structures called microcavities came into play, and people started studying experimentally these hybrid light matter states, and discovered many interesting properties of them, which distinguish them from pure light, from nonlinear optics, or from pure electronics. One spectacular experiment is this one on the observation of Rabi oscillations of exciton polaritons. So here you start with pure light. So you have a short pulse of light entering this semiconductor microcavity structure. So at the first moment of time, time zero, you have 100% light. Then it is absorbed. So this is the spectrum with two branches of polaritons. And with this short pulse of light, you simultaneously excite both these branches. And what you observe then it is the oscillations on the frequency given by the splitting of these two exciton polariton branches. So each of these modes is half light, half matter. Initially, you excite a superposition of them, which is 100% light. But then as time goes, because of phase difference between this and that state, the nature of this hybrid changes, and instead of 100% light, at some stage it becomes 100% matter, so full exciton. Then after half period, it comes back to light, then it comes back to matter, etc., etc. And this you observe because with a photodetector you can detect the optical component of this state, and you observe these oscillations that are called Rabi oscillations. Spectacular evidence of the fact that really you have a superposition of light and matter, and it is not immediately destroyed. It lives for some time. So, but what is this time? Time is on the horizontal axis. Here it is about 10 picoseconds, so not a very long time. And this time, the decay time, lifetime of a polariton is limited by a quality factor of the cavity. So how much time a photon spends in the cavity. And also there is the phasing linked with exciton. Exciton as a matter particle can interact with phonons, can interact with other excitons, with free electrons, etc. So it also contributes to the decay. And so the characteristic decay time is 10 picoseconds. Now, let me show you the results obtained in our laboratory in St. Petersburg a year ago. And you also observe here oscillations. Yes, they are detected by strict cameras, so also oscillations of intensity of light. But you see the time scale, thousands of picoseconds. So it is significantly more, at least 2 orders of magnitude longer life. What happened actually? What is the difference between the experiment on the previous slide, this one, where decay time is in units of picoseconds, and the experiment on this slide where decay time is in hundreds and thousands of picoseconds? The sample is essentially the same. It is not like the structure is of much better quality. No, maybe even the quality factor of this cavity is lower. No any difference in the structure. The difference is in the way how the state that exhibits these oscillations was prepared. So in the first experiment with Rabi oscillations, it was just resonantly excited by a short laser pulse. Yes, so a short laser pulse was centered more or less at the frequency of the excitonic transition, so it resonantly excited two polariton modes. In contrast, in this experiment, the frequency of excitation by laser was much higher than the frequency of polariton modes. So you did not excite polaritons directly by light. Instead, you created clouds of electrons and holes which lived their life. After some time, they formed excitons, Exciton is electron-hole pair bound by Coulomb interaction, polariton mode. So what happens that is that becoming exciton polaritons, they formed a Bose-Einstein condensate of exciton polaritons. So a state where in a single quantum state you can have maybe 10,000 particles. So in the same quantum state. I will talk about this phenomenon, which is very interesting, just in a minute. But now let me only address the phenomenology. So this is the difference. On the previous slide, we did not have the Bose-Einstein condensate, and the coherence time, decay time was 10 picoseconds. Here we do have a Bose-Einstein condensate, so we have many, many particles in the same quantum state, and the coherence time is several orders, 2-3 orders of magnitude longer. So Bose-Einstein condensation appears to be a key tool to enhance coherence in this system. And this is, I would say, counterintuitive. Because usually we tend to think that when we have many objects, it only brings disorder. Yes, with one car you can still drive, you know, from around St. Petersburg, but if you have 10,000 cars on a road, you will have traffic jams. But not, in this case, it is exactly the opposite. The fact that instead of one small number of polaritons, you create a state filled with thousands, tens of thousands of polaritons, somehow it enhances a coherence of this state. So let us discuss it a little bit further. And it brings us to the concept of polariton lasing, which was formulated in '96 by Imamoglu and Yamamoto. And then it was implemented already in this century. So one of the first works of low temperature polariton laser, this one, group of Lesidang. And next year, they published the same experiment with some supplementary measurements of spatial coherence in Nature, and already in the title there was this word non-equilibrium. It was removed. They claimed that it is Bose-Einstein condensation, and it was published in Nature, and that started, you know, an avalanche of works on Bose-Einstein condensation of exciton polaritons. Before that, no one could believe in that. Now there are hundreds, if not thousands, of publications, and hundreds of research groups involved in the field. But at that stage, people modestly were talking about a laser that is different from any conventional laser in a sense that it does not produce, there is no stimulated emission of radiation in this laser. Radiation, light is emitted spontaneously by a microcavity structure. But anyway, this spontaneously emitted light is coherent because it is generated by a bosonic condensate of exciton polaritons formed, you see, due to some energy relaxation of polaritons to some quantum state where they accumulate in huge quantities and they emit light. So as they are all in the same quantum states, they also emit photons that have the same frequency, the same polarization, and they are phase locked. So this is laser light. And polariton lasers, theoretically, they have no threshold linked to the inversion of electronic population. There is no inversion of electronic population, and there is no need for stimulated emission of radiation. Even if you put just two particles in the condensate, they will be coherent, and they will emit two coherent photons. So the threshold of polariton lasers is very, very low. However, well, it is probably not enough because polariton lasers are low power lasers, and they are still like looking for the niche where there is no industrial production of polariton lasers, as far as I know. But as it turns out, after these first pioneering works, polariton lasers appeared to be a fantastic playground for applications in logical devices, in logic circuits, and in quantum computation, which will be the focus of my talk today. So let us remember that, okay, these are polariton lasers, then this is very similar to what people observed in cold atoms, where they detected these bosonic condensates of rubidium or sodium. The difference is temperature. Bosonic condensation of cold atoms was discovered at temperatures close to absolute zero, at nanokelvin temperature range, while in polaritons we talk about much higher temperatures, including room temperature. So it actually depends on the semiconductor material which you use, but if you have a semiconductor that sustains excitons at room temperature, then you can, in principle, observe Bose-Einstein condensation at room temperature. And indeed, it was observed. These are the first works, and phenomenology is very, very similar to what people observed in clouds of cold atoms. Just it happens at room temperature. So you have all criteria of Bose-Einstein condensation satisfied on Sanger-Penrose, you have macroscopic coherence, etc., etc. So it looks like an interesting fundamental discovery, but initially people didn't know what to do with that. And they were just trying to see everything that they could see. One thing was to generate a trap. You can generate this, for example, parabolic trap optically with also two laser beams, and you observe quantization of the polariton condensate. You observe it with your own eyes. So what you see is the wave function. Yes, these are the wave functions. You can analytically obtain them solving Schrödinger equation and a parabolic potential. And so this is first energy level, second, third, etc. They're equidistant, and you can observe them because there is a lot of particles. There are bosonic condensates on each of these states, and they emit light. So you detect this light, and you detect these wave functions. Interesting. What can you do with that? Let us move further. Next step was to discover superfluidity, phenomenon known in liquid helium, Kapitsa works. So a flow without viscosity. Polaritons are usually called quanta of liquid light. So they flow, they interact with each other. That is why it is liquid, like molecules of water interact with each other. But it is also light because polariton is half light, half matter. So when they form bosonic condensates, it was shown that they exhibit properties of a superfluid. So again, there is no scattering, no elastic scattering until you propagate a defect through this condensate with a speed that is less than some critical speed, speed of sound, like in liquid helium. And it has various features of superfluidity. For example, you can put them on a ring, like this guy, David Snook, in Pittsburgh did. He created a trap in the shape of a ring, and he placed a condensate of exciton polaritons in the ring, and then he kicked this condensate with a short laser pulse. So this gave momentum, and the polaritons started moving around this circle. That could have been experimentally detected with optical interferometry. But the funny thing was that this motion was without any decay. So he kicked it once, and then for all time he was measuring, there was no any dissipation, no any loss of speed. It was just moving, moving, and moving, like it should happen with a superfluid. No dissipation, no viscosity, just permanent motion. And it is also similar to what we observe in superconductors. Yes, in a superconducting circuit, you can place it, well, if it is kept in a sufficiently low temperature, then for many, many years, the current can circulate without any external voltage and without any losses. So this already brings me to the main message of my talk today, which is that polaritons are very, very good candidates for realization of qubits. And they are these very good candidates because they are similar to Cooper pairs in superconductors, but better. Better because Cooper pairs, they require very low temperatures, And superconducting qubits, they operate at 100 millikelvin temperatures, but polaritons can exhibit superfluidity at room temperature, and they are fully optically controlled. So let me briefly tell you how we realized. So that was an idea formulated about 4 years ago when I worked in China, and then it was vigorously implemented in both in China and in Russia. Now there are this work develops in parallel in a network of Chinese universities and network of Russian laboratories, and I believe we are a little bit we have some advantage in Russia in what concerns scaling up of the structure and implementation of many qubits, but China is better supported financially. So who knows who will win eventually? But the concept is that, okay, let us compare superconducting qubits and superfluid qubits. They are very similar. So to make a qubit, you should quantize something. Yes, a qubit, Q comes from quantization. So you take two energy levels of something that is quantized, quantum object, and then you study the superposition of these two energy levels, the superposition state. This is a qubit. In superconductors, you can quantize charge or you can quantize phase. These are two conjugated variables. In superfluids, polariton lasers, cold atoms, there is no charge. They're electrically neutral, but the number of particles plays the same role. Actually, charge is proportional to the number of Cooper pairs. Here we can quantize the number of polaritons or the phase. So in superconducting qubits, both ways have been exploited, and the most popular is charge qubit or transmon, but also phase qubits have been implemented, fluxonium, and some of their characteristics, fidelity is better than charge qubits. In polaritons, the proposal for the number qubit was formulated and studied in Singapore, in particular by Tim Liu and Sanjeev Ghosh, but it was not yet experimentally implemented because a single polariton has a very short lifetime. If you make a qubit based on a condensate and condensate plus one excitation, then the lifetime of this qubit would be limited by the lifetime of this excitation, which is 10 picosecond. And then you cannot do much with that. But flux qubits appear to be much more robust. So this is the first theoretical proposal, which is based on this same idea of a circular trap, like in Snow experiments. We know that we can induce superfluid current in a circular trap. It would not decay, so it is very robust. It can exist for hours or longer until you keep pumping. And it is quantized because the momentum, the phase of this superfluid flow is quantized. When you go around the circle, you may only change your phase by an integer number of 2 pi. And this gives you a discrete spectrum of quantum states. So take 2 of this spectrum and make your qubit on these 2 states. For example, on the states corresponding to clockwise and anti-clockwise currents. And their superpositions would give you the basis exactly like it happens in the superconducting flux qubit. So now what happens experimentally? Experimentally, first of all, you need to create a trap, right? To have this ring condensate, you should create a trap. You can do it different ways, but the most flexible traps are created optically by non-resonant laser light. With special light modulator, you create a potential in the shape of a ring, and this excitation creates a cloud of electrons and holes. They repel polaritons. So for polaritons, it is this kind of structure, like a stadium. Yes, this is a trap. And there is quantization of polaritons inside the trap, and you can study quantized states and choose 2 of them and make a qubit in the trap. Then, in order to control this qubit, perform logic operations, then you need some control pulses that would create temporary potentials, like perturbations, that would induce transitions in this spectrum from one state to another, or from one superposition to another. That was the starting idea. This is the experimental setup that was built at SOLAB in St. Petersburg University. And this is how it works. First of all, they managed to observe many discrete quantized states in a circular trap. These are the states. L is the angular momentum that is quantized. And you have the ring is the emission of the trap because it also emits light, but at some different frequency from the polariton mode. And then images inside are wave functions of confined quantized polariton condensates in a trap. So we have many of them. We can choose those that we like. And we like actually these two. You see 2 pi x and 2 pi y states. In an ideal circular trap, they are degenerate. They have the same energies. But if you make trap slightly elliptical, you can create a gap between them. So one that is aligned along the main axis of the ellipse would have slightly different energy from one that is aligned along the short axis of the ellipse. And you can control the splitting between two of them, changing the ellipticity of your trap. So this splitting, anyway, it is in a micro EV range. So it is much less than the splitting between these two states and all other quantum states in the trap. So basically, you can forget all other states and work with these two because all others are very fine energy. The same happens with superconducting qubits. They select from an infinite number of discrete levels. They select two that are closely placed on the energy axis and which are sufficiently isolated from all others. So we work with these two states. And what we do? First of all, we want to create a superposition of them. Initially, the system sits in one of these two states, for example, pi x, so this state. So we need to kick it in order to create a superposition. And we do it with short laser pulses, femtosecond laser pulses. And actually, it turned out that in order to strengthen the effect of a pulse, you need to use a train of pulses. So here are 8 pulses that come one after another with carefully calculated spacing in order to provide a resonant effect. And with this, really, you move your state from one of the eigenstates of the trap to the superposition state of the trap. And when you do it, when you have a superposition, you can observe, first of all, Rabi oscillations, which already I have shown you some images. You see how in real space your condensate oscillates. So this donut, it is an experimental image obtained with strict camera. And it is a superposition of this pi-shape wave function, pi x, which is horizontal, and pi y, which is vertical. When you put them together, it gives a donut, but still you see oscillations because your trap is elliptical. There is some splitting between them, and you see oscillations on the frequency given by this splitting. You can see it in real time, and these oscillations do not decay for a long time, more than 2 nanoseconds. So this is much longer than the single polariton lifetime, and it gives us hope that the system is robust. Actually, Bose-Einstein condensates, as I told at the very beginning, they are much more robust than individual polaritons. And qualitatively, this is because an individual polariton can just disappear. But when you have 10,000 of them, one goes out, one comes in, and the whole bunch of particles, they still carry on. They keep their phase, they keep their macroscopic properties. So as the Russian song says, Отряд не заметил потери бойца. Яблочко песню допел до конца. Вот this is what is going on here. These oscillations should be distinguished from characteristic limit cycle behavior that is observed in many nonlinear optical systems. So in a limit cycle, the frequency comps should be observed, and the frequency of bits is dependent on the nonlinearity. Here it is not the case. Nonlinearity does not play actually any important role here. The splitting is perfectly, this frequency is perfectly fixed by the geometry of the trap, and it is tunable. We can control it experimentally. We do not observe any attractors characteristic of nonlinear system. We do not observe frequency comps. So the phenomenology that we observe is well reproduced by a linear model based on linear Schrödinger equation for a two-level system. Just two energy levels, quantum bits of these two levels, and this explains everything that we observe. Okay, then people from quantum technologies, they are very worried about coherence times, T1 and T2, because this defines how long a system can be used for quantum computation. So here it was measured with time result interferometry. We could probe separately two basis states of our qubit, this one and that one. And also the green circle is in the overlap region, where we probe the coherence between them. So far the times are 1200 picoseconds T1 and 750 picoseconds T2. And is it long or short? It depends. It should be compared with a characteristic time needed to perform a logic gate operation. So in this system, it is of the order of several tens of picoseconds. So it is at least this ratio of coherence time to the time needed for a quantum operation is of the same order as for fluxonium superconducting qubits. But here the superconducting qubit, it performs one operation in several tens of microseconds. And here several tens of picoseconds, so 1 million times faster. Okay, now I will move faster. So operations. So we initialize the system, we control it with laser pulses, we calculate with actually Schrödinger equation, we calculate where we need to hit with a control pulse, and we map the dynamics of the system to the Bloch sphere in order to see if the required operation is implemented. This allows us to obtain the fidelity of quantum operations that we realize. So here, for example, for the Hadamard operation described by that H operator on the top, we obtain a fidelity of 95%, and it is averaged over 6 different initial states. So we probe different initial states on the Bloch sphere. We always use the same gate, so the same control pulse, and we see if the results, how much the result deviates from the predicted one. And this gives us the fidelity, so 95 for this operation, and even more, it was a 97 for Pauli Z operation that actually corresponds to the 180 degrees rotation around the axis of the Bloch sphere. Here the experiment was done very carefully with 20 initial states examined. So this fidelity is approaching the fidelity of superconducting gates already. But you see, a single qubit is not sufficient to make a computer. You need at least to demonstrate double qubit gates. And in the remaining minutes, I will show you it. So for double qubit gates, we need 2 traps. So much more modeling, much more careful analysis of the spectrum of these 2 gates. So we select again the group of states. These are eigenstates of 2 traps together. They are coupled by tunneling of polaritons. And to describe it, we need to solve a two-body Schrödinger equation. So it is not one qubit, it's two qubits, and we count for reservoirs, dissipation, etc. So we describe the system with some density matrix, reduced density matrix, 4 by 4 with these basis states. We do theoretical modeling to predict fidelity of these gates, gates like C0, I-swap, and others. And then we implement it experimentally. So here the great important issue is readout of the state of the system, because we need to detect simultaneously in our experiment 16 elements of this 4 by 4 density matrix that characterizes two qubits. And this can be done by time-resolved interferometry, where the images, interferometric images, which change in time, they are fitted on the basis of 16 interferometric images corresponding to 16 elements of the density matrix. So this technique allowed us to attempt to demonstrate a quantum entanglement of two polariton qubits. And this is a holy grail. Actually, people are skeptical about polaritons. They say, oh, you have dissipation of system. Probably you lose coherence, so it is probably classical. It's probably not qubit. It is probably some analog thing. Well, superconducting people, that's true that they also have many particles, but you know, great superconducting community, they spend so many years working on that, so we believe them, and we do not believe you, youngsters, polaritonic people, bandits who intervene in the field and say that they are better than others, but actually we are not. You're probably cheating, so show us a quantum entanglement. So after all these discussions, we really decided to put an effort. We studied this entangling operator that moves our state from a pure state to an entangled state. And we read a lot of papers on the entanglement of bosonic condensates, including bosonic condensates of exciton polaritons. And we concluded that, again, counterintuitively, surprisingly, the more particles you have in the condensate, the better it is for entanglement. So when you have many particles, it does not break coherence, it doesn't break entanglement, but it strengthens entanglement. And the measure that characterizes an entangled state is the negativity, the property of the density matrix of the system that we measure. So we decided, first of all, we did numerical experiments. We decided to see which operators, which perturbations may lead to the build-up of negativity. So negativity equal to 0, it means it is non-entangled system, but if it deviates from 0, then it means that you have some entanglement. And it can grow up to 0.5, which corresponds to the belt state, the most entangled state. So initially, you see this is very small deviation from 0, 0.08, but with some effort, careful work, we actually achieved the geometry of these control pulses. Two control pulses are needed to achieve the negativity of 0.5, theoretically. Yeah. Okay, so then experiment is always more tricky than theory. In theory, with this entangling operator, we move from this pure state, this is the density matrix, to this bell state, the bell state. So equal amplitudes here in these 4 elements of the density matrix and 0 everywhere else. This is a state of maximum entanglement, famous bell state. Now, in the experiment, it is not so good. Even the initial state, we were struggling to initialize the system in such a pure state. So we still had something here. And the final state, at this stage of experiments, work in progress, it is also not exactly Bell state. Experiment is experiment, but if we look at the negativity, the experimental negativity with all noise, etc., you see it achieves 0.3. Yes, the theoretical maximum is 0.5. So this makes us optimistic. This makes us thinking that we are on a good way towards implementation of really quantum networks based on exciton polariton condensates. And this is what we want to do. So here are my conclusions. So far, we realized single and double qubit gates. Our Chinese colleagues realized a universal single qubit gate, and they are working on double qubit gates. We perform logic operations due to the control laser pulses. We developed the readout scheme. We show that the coherence is preserved on a time scale strongly exceeding the polariton lifetime. And very important benchmark, the quantum entanglement of two qubits has been achieved. So then next stage would be scaling the system up, going to 10, 20, 100 qubits. And in principle, it is straightforward with use of special light modulators because all these traps are optically induced. You do not need to grow a new sample. You just need to use a new code in your special light modulator. So with this, I would like to acknowledge people who actually did this work. So the experimental part was realized by the group of Roman Cherbunin in St. Petersburg State University, and the theoretical part was realized in the Abrikosov Center in Moscow by Andrei Kudlis and Denis Novokreshenov. And I thank you very much for your attention.
Thank you for wonderful talk. So we have a few minutes for some discussion.
Okay, thanks a lot for a very interesting and educated presentation. But let's go to slide number 20. It's just a very simple question about the experiment. Strict camera, probably this one, okay? Yeah. Let's strict camera recorded light. How many photons they recorded? Or another question, what's the concentration of condensate were used in this experiment?
Yeah, thank you for this question. Indeed, it's very important. So this is a strict camera Hamamatsu in synchroscan mode. It was initiating the system with a laser pulse. Then it was detecting within some slit the signal, which of course it was not single photon detector, so many photons. And then it was also averaged over about 1 million of pulses. So we were creating the system million times. So altogether, what we measure can be called quantum tomography because it is averaging over a million of experiments.
Okay, thank you.
Thank you very much, Alexey, for the interesting talk. So I have a question just to make sure that I understood correctly. So is it true that you could easily make identical polariton qubits because you're using the same spatial light modulator and you could replicate them multiple times?
Yes, so that's also a very important question. And the answer is yes and no. So of course, these traps are macroscopic. So it is not like atoms. So they are, in principle, they are theoretically different. There are always fluctuations, etc. However, what is remarkable about polariton system is its incredible ability to phase lock. So here I refer to works of Pavlos Lagoudakis, who put more than 1,000 condensates on a plane of a microcavity, and he observed a phase locking in a system of spatially separated 1,000 condensates. Of course, they were of different, slightly different. There were always deviations in the number of particles, but system is able, due to this tunneling coherent interactions, to form states with extended coherence. So coherence length is much larger than the size of the system. Here, with 2 qubits, what we did, we on purpose, we first detuned them to have 2 independent qubits, and then with optical pumping, we brought them with a pulse to the resonant state where they are phase locked. So we can switch on and off coupling of 2 qubits. How it will be with 20 or 100, I don't know yet. It needs to be developed. But when we have 2, we can be confident that they can be brought to the fully coherent state.
Thanks a lot.
Okay, yeah, we are run out of time. But before thanking our speaker, let me give you.
Oh, thank you. Thanks a lot. Thank you very much.
Yes, wonderful talk. And yeah, so I will give the honor to be a chair of the session to Professor Vartanyan. So please.
So next talk will be given by our sponsor. I want to present Artur Gaugel from InScience, who will tell us about the prototyping of optical system using the special equipment which they produce. Please.
Greetings all. Thank you for your time. My name is Artur Gaugel, and I represent InScience. I'm the product manager for the JCOPTIX brand, and I'll briefly introduce JC and showcase real examples of how JC products help customers solve their challenges. At the end of my presentation, I'll be glad to answer any questions you may have. So let's start. JCOPTIX was founded in 2017 on the basis of the Liquid Crystal and Photonics Technology Research Center at Nanjing University. Initially headquartered in Suzhou, but the company relocated to Nanjing in 2021. Much of JC's management's team consists of former Thorlabs employees, ensuring that their products are fully compatible and interchangeable with Thorlabs components. And I understand you might reasonably ask, how does this Chinese optomechanics brand stand out in a market flooded with alternatives in Russia? That's partly why I'm here, to dispel any preconceptions you may have about this equipment. Firstly, I've visited JC's production facilities, clean rooms, and warehouses, and I can attest to their high standards. It's not just about the manufacturing equipment, though that's impressive too, but their quality control is far ahead of competitors. Beyond that, their after-sales support is exceptional. I'm really proud of our collaboration with JC. Every piece of feedback, reviews, or comments from us or our clients is heard and addressed. Also, they are also open for custom solutions. Right now, their catalog includes several products developed in response to customer needs. And the last one, JC also doesn't just talk about advancing science, they act. In December 2023, they launched a quantum technology development platform, hosting monthly conference at Nanjing University with guest speakers. They've also introduced a grant program for quantum researchers. In April, InScience participated in Photonics exhibition in Moscow. We had large booth filled out with from 5 JCOPTIX tables with optical system on them, and all systems were assembled from JCOPTIX components, and also we had one major system. This system is our engineer's modular multifunctional microscope, integrated 8 instruments into one device, from confocal microscope and luminescence spectrometer to laser tweezers and linear interferometer, all using JC's 30mm cage systems. Yes, as you can see on the slide, this development received recognition at the exhibition, but that's not all. Also, here are 2 real cases from our customers. The first one, let me introduce the work of the Scientific and Technological Center of Unique Instrumentation, represented by Olga Polshikova. This optical system was assembled by their team using components from JCOPTIX and Thorlabs. In our work, among all the cases, this the most popular one, to add some JCOPTIX to ready-made Thorlabs systems or replace some Thorlabs components. In my opinion, this is an excellent demonstration of component compatibility. The very first components along the optical beam paths are JCOPTIX kinematic mounts for KH system with SM standard reading for 1-inch optics. The customer already had Thorlab's cage system rods, and these components matched perfectly. Next, they used compact JCOPTIX kinematic mirror holders. Since this system utilizes two light sources, it required a switching mechanism between them. For this purpose, they employed JCOPTIX flip platform, which demonstrated high stability and reliability, ensuring precise beam trajectory. The light is then spectrally filtered by an acoustical optic tunable filter, focused and passed through apertures, resulting in two diffraction orders at the output. One order is directed to a spectrometer via JCOPTIX mirror mount, while the other is used to generate a color stimulus. To create color spots of varying diameters, multiple configurations are used. Switching between these configurations is done using JCOPTIX flip platforms equipped with JCOPTIX lens doublets. The beam is then projected onto a matte plate and displayed for the participant for colorimetric researches. And the second one, another example, is work by Vladimir Fedorov from the Alexey V University in Saint Petersburg. In this case, a system was developed to expand the spectrum of available sample excitation methods. This includes femtosecond laser excitation for researching nonlinear properties of semiconductor nanostructures and monochromatic excitation at arbitrary wavelengths. Since the light exiting the monochromator has different divergence and vertical and horizontal directions, in addition to a beam expander, Vladimir implemented astigmatism compensation system using cylindrical lenses. Also, filter wheel was also added to eliminate parasitic harmonics and pump diode radiation during experiments. For polarization resolved researches, the system includes a wave plate. To research the optical properties of nanostructures, beams with non-trivial polarization like Gaussian beams, for such beams, the first order vortex plate was installed, enabling azimuthal and radial polarization. According to Vladimir, the use of a cage system with quick release mounts made this system highly convenient in practice. Of course, these are far from all of JCOPTIX customers. Despite the brand being relatively new in Russia, we have already solved numerous challenges. In addition to supplying optomechanics and optics, we have also implemented deliveries of JCOPTIX optical tables and other laboratory furniture. Yes, for example, as you can see on the slide, Konstantin Lyakov from MIFI is assembling an interferometer on one of the optical tables we supplied to them. There is a lot of equipment available in our warehouse right now. You can contact our managers at any time to update the availability of goods. We will be glad to cooperate with you. You can send us the list of the necessary equipment, or you can just describe your task to be solved, and our engineers will select the equipment for your research. Moreover, you can take samples of products to test in your laboratory. For my part, I can promise you that we will offer you the best conditions on the market. After the formal part of this event, my colleagues and I will be able to discuss your task and your projects. I look forward to a productive and mutually beneficial discussion. Thanks again for your time, and thanks a lot for your attention.
Thank you, Arthur, for nice presentation. If you have any questions for production? No? Not the case? So, when we go to the next plenary talk, it will be given by Professor of ITMO University, Sergey Makarov. He is also establisher of a new brand laboratory in China, and also a trader of numerous scientific awards, and also he is my boss. So it is my pleasure to invite him to the stage. Please come.
Thanks a lot for the kind introduction. Yeah, my name is Sergey Makarov, and today I'm going to talk about some, on one hand, new direction in material science about perovskites, and also combined with some quite familiar for this community direction like a femtosecond laser ablation. And first of all, I would like to also acknowledge and mention that here we will have a lot of results which we have done together with our cooperators like internal at ITMO University and also external. So there are some names and especially some bold font applied to some key collaborators, especially for these results. And there is an outline of my talk, so I will start from some general introduction about perovskites and femtosecond laser ablation, then some applications, some cases how we can apply laser ablation of non-perovskite materials to supplement perovskites to show some applications, and also finally how we can apply lasers, femtosecond lasers to process to modify halide perovskite directly. So first of all, we have to start from this important work from Boris Chichkov team from Hanover University in Germany. So here they showed clearly the difference between nanosecond laser ablation, femtosecond laser ablation. So indeed, thermalization time is close to electron phonon coupling, and usually it's like on picosecond scale. So, and if we apply femtosecond lasers, we have much shorter time than thermalization, and that's why we have very small heat affected zone. This is very critical for nanotechnology if we would like to apply femtosecond lasers. And of course, I have to mention that in this community in Russia, so we have several strong teams, and actually even more, I mean tens of very strong teams. Let me just highlight several of them who actually really applied femtosecond nanotechnologies for different directions. But anyway, yeah, recently we can say that there is a new paradigm in femtosecond laser technologies when we shouldn't tell only about physical processes like excitation, Keras relaxation, Auger recombination, thermalization, melting, evaporation, and cooling. But also in parallel, we have to consider many chemical processes in the material. So especially if we are working with some materials which support some photochemical reactions, or liquid material, when we can generate initiate some chemical reactions during the laser ablation process. And one of such bright example is laser processing of halide perovskites. So what is halide perovskites and why they are so important nowadays? So generally, perovskites belong to general family of materials called perovskites. The first example was found in Ural Mountains in 19th century by German mineralogist Gustav Rose, who was sponsored by Lev Perovsky. That's why this material is called perovskites, after the name of Lev Perovsky. And then this structure was described by Victor Goldschmidt, and he just showed that this is big family of materials. But halide perovskites is the case when we have halogen on the end of the formula of ABX3. So it can be all inorganic perovskite, organic inorganic perovskites, and then only 15 years ago they become very attractive for optoelectronic community when Professor Miyazaki from Tokyo University just showed that halide perovskite can be applied successfully for solar cells, and created first solar cells, and now the solar cells have very high efficiency, even better than silicon. And also just a few years after that, perovskite light emitting devices appeared, and also perovskite micro nano lasers also appeared just 10 years ago. And the perovskites, the family of halide perovskites, it's a family of semiconductors. So it's direct band gap material, resembling sometimes gallium arsenide, but much cheaper. And you can just synthesize them chemically. So it's a very cheap approach. And also their optical properties is shown on right upper diagram. And there you can see that this is mid-refractive index material. So refractive index is lower than for silicon and gallium arsenide, but higher than for glass or polymer. So that's why we can have good optical contrast if we are creating some nanostructures or optically resonant or waveguiding systems. It has very good absorption, even better than gallium arsenide. That's why it's very promising for photodetectors, for thin film photovoltaics, and they emit light. It's direct bandgap semiconductor with strong exciton at room temperature, and also interestingly that this is so-called defect tolerant material, and it means that if we after processing of the material, after aging of the material, we have not deep defects but more shallow defects. So the carriers can be trapped at room temperature, and still we have a high quantum yield for photoluminescence. Also, there are some interesting properties of such materials. They can be low dimensional, they can be layered, and people call it 2D perovskites. And here, why it's important, because we can play not only with composition of perovskite to tune band gap and tune the emission wavelengths in the whole visible range, but also we can play with thickness of this layer of two-dimensional materials to play with quantum confinement, and also we can tune luminescence, emission wavelengths in the whole visible range as well. Yeah, there are also some interesting effects like giant anisotropy and a lot of phase transitions, also which people use in laser processing of the material. So that's how we can. So that's what we know about this material. And also, as for optoelectronics applications, and especially for such applications like transistors or light laser diodes. So there are some critical parameters like thermal conductivity and mobility of charge carriers. So mobility of charge carriers and perovskites are quite good. So they are also comparable with the family of the standard semiconductors like 3, 5 to 6. But thermal conductivity is much less. It's close to glass, even less than glass. So on one hand, it's bad for, let's say, if you would like to create some high power device, yeah, because of overheating problem. But from the point of view of laser ablation, it's good. I will show you many examples how we can employ this. And what kind of samples can we create made of perovskites? So, of course, we can create large scale, centimeter scale, microcrystals, not macrocrystals, and also microcrystals. You see that the scale is around 1 micrometer or less than 1 micrometer. So we like such objects when we use them, apply them in nanophotonics and nanolasers. But also nanocrystals is huge family also of, big direction now, because they can be deposited easily on arbitrary surface and emit light very efficiently. So quantum yield of this nanocrystal is very high, so more than 90%. And of course, bulk perovskite, but deposited as a thin film, also is very popular in photovoltaics. And there are some examples from our lab. So let's say we can synthesize these quantum dots of different colors, and there are some examples how we, in partnership with our industrial partners, with printing companies. So you see here some examples of how perovskite inks, how they're bright under UV illumination. And also different methods of deposition can be applied, inkjet printing or some other methods of printing. So here you see some beautiful examples. And also we had some project on the creation of such kind of smart windows. So here you also see that when we deposit halide perovskite between two glasses, then we can excite them by LEDs in frame of this frame, you see, and then the emission is really ray emission is very bright. So you see that it can be it can just even block face of this EDIC. And also there are some examples of incorporation of halide perovskite nanocrystals inside some polymeric based like chess pieces in these cases, so they can be of arbitrary shape. And then in collaboration with our microwave department at ITMO University, with Polina Kapitanova team, we developed such a nice prototype for wirelessly powered halide perovskite quantum dots. And but generally, as I mentioned, there are two key directions of applications in halide perovskite direction. Perovskite solar cells, which are now becomes very high efficient. So you see, if you compare this blue curve, which is actually like a straight line, without any progress for silicon, and also rapid growth of efficiency for perovskites and now perovskite solar cells. Single junction is higher than for silicon, and also if we consider perovskite silicon tandems, so efficiency now more than 33%. So and we have already, I mean, we know about many startups and some companies in Europe and China. So, and we believe that in near future there will be some companies commercialized solutions for perovskite solar cells. And for perovskite LEDs, it start to be developed a bit later. So that's why the progress is, despite the very expiring progress in this direction, also you see this dashed line corresponds to threshold for commercial usage of LEDs, from the point of view of efficiency and lifetime in hours. So you see the different colors of perovskite LEDs. They are growing and green, one of the most stable. They are approaching this threshold, but still, there are many works to do to achieve this threshold. And also our team is actually actively working in the field of photonics with perovskites and nanophotonics. So we just combined some disadvantages of perovskites with some needs from the photonics community. Like we focused on micro lasers, waveguiding systems, some metasurfaces, and try to apply these nanophotonics approaches for such devices as solar cells I will show you today, and some nanolasers. So let's start to overview our recent results and start from laser ablation of non-perovskite materials which are combined with perovskite. So let's start from perovskite photovoltaics. And generally here the idea is that if we have perovskite solar cell, we want to improve this efficiency not by some complicated chemical methods and many optimizations in architecture, but if we want to introduce some nano antennas, some non-perovskite resonant nanoparticles. It can be plasmonics, it can be all dielectric nanoparticle. And first work was published in UK in 2013. They introduced plasmonic nanoparticles inside, but the problem with plasmonics that the high losses in the nanoparticles and also chemical reaction between metals and perovskites. So that's why the efficiencies of this, improvement was not so high. But then in parallel, new field appeared, like all the electric nanophotonics in visible range. And based on these two works, so we also were inspired by the approach when we can also tune resonant properties in nanoparticles, but not in plasmonic nanoparticles, but in silicon nanoparticles, which are quite easy to produce by laser ablation. So these two examples actually from the people who are from laser ablation community, and they really affected a lot the nanophotonic community. So this is a very good example for us. And in our lab, we used laser ablation as well to create such nanoparticles, but to create them in the liquid. Yeah, so this is a very well-known technique, laser ablation in liquid. Here are some example of the bottle with silicon suspension of colloidal solution with nanoparticles of different size distribution, and then after deposition on the surface we can have such a distribution of nanoparticles, and we can play with concentration. Each nanoparticle has scattering spectra, as you can see here. There are some calculated values also we measured a lot. And it means that we can cover the whole visible range. So they scatter light in the whole visible and near infrared range. So here are some examples made by our former PhD student Alexandra Furasova. Today she will also give a talk about this direction. So I will just briefly mention it. That yeah, in perovskite solar cells we can introduce such nanoparticles and improve actually absorption and eventually efficiency. So also the nanoparticles can be not just with broad size distribution, they can be of different sizes. So we can select particular size, and you see after selection each nanoparticle color, each solution has different color because of resonant light scattering in each nanoparticle. And it's also a good approach for creation of colorized solar cells, which are good for building integrated photovoltaics and for some design approaches. And also, in principle, laser ablation is quite universal technique. We can use not only just standard silicon, we can use doped silicon, and with doping we can play with mobility for carriers through such nanoparticles, and also improve carriers harvesting. So generally there is a chart of evolution for in this direction. So evolution of efficiency improvement in perovskite solar cells, and you see this gray bars corresponds to all the electric nanoparticles, and this yellow bars correspond to plasmonic. So we see that so far improvement by all the electric nanoparticles has the best result in this direction. And of course, we can think about not only silicon, not only metal, but many other materials like two-dimensional materials. And so you know better than me, yeah. So how many materials can be formed can be ablated in form of nanoparticles. So, and yeah, for more details, please visit today Alexandra Furasova talk. So she will explain in more details how nanoparticles can be applied for perovskite solar cells improvement. And let's go further to photodetectors. So how we can apply laser ablation for photodetectors. So here our collaborative works with Professor Albert Nasibulin from Skoltech, and his nice carbon nanotubes. They are in form of sheets which can be cut by laser very carefully, especially if we work with flexible substrate where we should cut it to don't damage, to don't change too much the substrate properties and smoothness. And here, after the cutting precisely by femtosecond laser, this single volt carbon nanotube films. So then we deposited the solution with precursors, and then after that we grew perovskite single crystals, and then in principle we can apply voltage to such system, and we will have photodetectors. So here you see these big cubes formed microcubes. So this is actually the size of each cube is around 10 micrometers. And then after growing, the contact is very good because they grew on top of these nanotubes, and the quality is quite good. And then we created this such flexible photodetector with quite good responsivity and reproducibility. So after many bending cycles, this device is still working well because of very good contact between perovskite and single-wall nanotube film. Also, yeah, let's go to direct laser ablation of perovskites. And yeah, let's start from first works in this direction. So this laser printing of perovskite nanoparticles. So we initially in 2014 the first demonstration of printing of dielectric or semiconductor nanoparticles was demonstrated in again Professor Chichkov's team in Hanover. He printed very nicely this array of nanoparticles, then even anneal them and change their optical properties. And then we just also modify this method of printing at ITMO University and further studied their nonlinear properties and so on. So this technique is really really very useful tool for creation of nanoparticles on substrate. And we just 1 year later we applied laser ablation in air, yeah, and deposition like printing on substrate for perovskites of different composition, which emit light in red range, in green range. And interestingly, that such technique, if you want to apply it for light emitting semiconductor, if we use, let's say, gallium arsenide or indium phosphide or any kind of 2635 semiconductors, after such laser ablation, they wouldn't emit light efficiently. So because we generate a lot of defects, but because perovskite is defect tolerant material, that's why direct ablation doesn't destroy perovskite and it's not so harmful for photoluminescence. And also again we have resonant properties for such nanoparticles. So we printed different nanoparticles, calculated their scattering efficiency, and also we studied their emission properties. And emission is even enhanced because we still have photoluminescence, and also we have cavity. Yeah? Like Professor Kavokin also told us that cavity is important for polaritonic effects. Here, cavity is important to couple in weak coupling regime our emission with like shape of this so each particle is like a self-resonating system which emit light and this light couples with material and resonates. And also, yeah, talking about weak coupling, so if we have excitonic material, so perovskites are excitonic material, we see that in refractive index we have this characteristic peak, and this exciton can couple with Mi resonance, and we can expect Fano resonant feature. So when we have broad resonant, Mi resonant, and narrow exciton, so after coupling, we can have a so-called Fano shape peak. And indeed, in our experiments, also in scattering, after printing of such nanoparticles, we see in each case in scattering, in optical dark field experiment, we see such a symmetrical peak where we have coupling of exciton, which is stable, the position is stable, but Mi resonances are size dependent. And around exciton, around 539 nanometers, we always have this asymmetric Fano feature. And now we are working on the gas sensing to employ this Fano resonance to detect different gases, which modify properties of halide perovskites. And the next part of work we did together with a team from Vladivostok, from Academy of Science, together with Alex Zhishenko and Alex Kuchmezhak. So they are also here at this conference. So we actually did a lot of interesting work together. So and we were motivated by the fact that halide perovskites, they are quite sensitive to standard techniques of for semiconductors because it's ionic material, and if you apply some liquid, it can be dissolved. Any polar liquid dissolves perovskites. and also there were some works on CW laser processing of perovskite, but light emission properties anyway and quality was not acceptable for many applications. So that's why we used a femtosecond laser pulse to make laser ablation much more precise. And also we use the fact that thermal conductivity of perovskite is extremely low. It's lower than glass. So that's why heat affected zone is really small. And some first examples showed us good quality of perovskite laser ablation. You see, if we compare silicon and perovskite, inorganic perovskite, cesium lead bromide, we see that at the same conditions we have different quality of the ablated region. So the same focusing conditions and the result is different. Here you see that for perovskites ablation is much more clean. And heat affected zone also is much less for perovskite as compared with silicon from our measurements. And we used, could you please click on this video if anybody sitting on the, можно попросить нажать на видео? So here you see some example how how fast can be printing of the micro lasers made of perovskite. We just deposit by simple method of wet chemistry deposition perovskite film and then apply donut shape femtosecond laser pulse and just print in few seconds. You can print tens of microdiscs, and just half an hour we can print a lot of microdiscs on the centimeter scale. So I don't know, millions or billions of microdiscs can be printed just during half an hour. So there are some optimization, and disk diameter can be different from several micrometers up to any scale. Again, so after the removal of material, light emission still for remaining perovskite, light emission is still there because of high defect tolerance. And projection lithography, femtosecond lithography allows to create different patterns. We can project the different shapes of light beam and then form different structures like gratings, nanoholes, and so on. And you see from this photoluminescence confocal mapping that luminescence of the remaining material is still the same like from the film around. So that's why why femtosecond laser doesn't. Clear demonstrations that perovskite still emits light very well after laser ablation. So here are some other examples how we can create nanowires lasers. So here not only microdisc but nanowires, and again they're very small, 500 nanometers in diameter, but still the remaining material is not affected. So heat affected zone is very small. And here recently also we studied how polarization affects the shape of a quality of ablation. So if we would like to use a laser scan mode, it's very important to keep in mind which polarization do you use. If you move in this direction, you have high quality like stripe. But if you move in vertical direction, let's say, it means that you can have a worse quality. So here you see why. Because for smooth surfaces doesn't matter, but once you create a crater and then shift it a bit your laser beam on the figure A, you see that if we for different polarization, if we shift our beam a bit to the right direction for different polarization, we have different field distribution and quality becomes a bit different. And to avoid such situations, sometimes it's useful to just to use a fixed period and use some, let's say for this case, we synthesize nanowires, perovskite nanowires, and then apply stripe laser beam to create a grating on top of it. So again, because of high defect tolerance and low thermal conductivity of perovskite, we can expect that we don't destroy other material on top of lower than such grating. and this grating is useful for a light outcoupling in vertical direction from nanowire, because usually perovskite nanowire, they works as a resonator and light emitting system like nanowire laser. But once we create grating on top, very shallow, we have leakage of light on vertical direction. So that's how we can change and optimize the outcoupling of light from such nanowire laser in vertical direction. So, and as an outlook for this direction, so we are working actively also on compact perovskite nanolasers because of their very high optical gain. We created very compact nanolasers, nanocubes by chemical methods, yeah. But chemical methods, they give random nanoparticles. That's why we want to apply femtosecond laser pulse to create as small as possible nanolasers made of perovskites, but it's very challenging. And also halide perovskites can be ablated by, as I told, different shapes of laser beam. And here it's useful also for thinning of the film. Yeah, here you see some example how after each pulse we can make film the thinner and thinner and control the thickness. And also gratings can be fabricated, and also such gratings can show nice diffraction efficiencies, and which can be used for encryption. Let's say for different direction of light illumination, we have different patterns. So this how it can work. And also in luminescence, here you see they have some pattern in luminescence, they have some pattern in dark field. So this can be used for encryption. And also as for encryption, we can also apply some two-dimensional material properties, as I promised you in the beginning that we discussed some phase transitions. And one of the interesting example is phase transition from two-dimensional perovskite to bulk perovskite. As you can see here, so we have different emission wavelengths for different number of layers, and if we and also different compositions also have different wavelengths. So we can combine these two properties to create some patterns on perovskite. So we just have quite complicated two-dimensional material like butylamine, methylammonium, lead, bromide, iodine, perovskite. The idea was to create such metastable material. Then if we illuminate it by quite relatively high intensity light, we can convert it from two-dimensional case to three-dimensional case, because we can evaporate some ligands and just make them material bulk. So, and it's exchange properties, emission properties. So if we have n is equal to 1, it's just a single layer material. But if we have multi-layer system, we can convert them to bulk and write some, and just each dot will emit light with different color. So here some example also of pictures which we created made of this material, and then in photoluminescence you see that each dot has slightly different color, created following this regime of draw programmable, in programmable way. So this how we used conversion of layer perovskite to bulk perovskite, and which change, we lose quantum confinement and we change the light emitting properties. So here I would like to overview our recent results. So if we use laser ablation for non-perovskite materials, so anyway we can apply them for perovskite solar cells, for photodetectors, and also if we directly process perovskites by laser, we can create some micro lasers, nano lasers, and do some encryption in perovskites. Also some outlooks, we are now actively working on perovskite LEDs. So this is work in our lab in collaboration with Alexey V University from Van Muchen team. So they provide us nice substrates, and we just created pixelated some display based on perovskites in green range. And in this case, each pixel size was around just more than 100 micrometers. But recently now, in collaboration with our Chinese colleagues in our joint center in China, so they use TFT matrix with much less pixel size. The pixel size is around 10 micrometers, so maybe 20 micrometers. But recently it was nice work from JCOPTIX University, from Professor Deva ED, and they showed recently that halide perovskites are very promising for nanopixelated LEDs, yeah, and they compared the different materials and showed that area of just less than 1 micrometer is a good area for halide perovskites. They used by lithography method. This is not for laser. This is not laser ablated yet nanopixels. This is made by lithography. You see many stages we applied to create such nanopixels, and I think it's a good challenge also for us to create such nanopixels by much cheaper technology like laser ablation. So just the last slides about some announcement. Also, we are very welcome you to apply to our conference in Qingdao, organized by academician Yuri Kulchin. And it's a nice place also to continue our discussions in the field of laser technologies and optoelectronics and nanophotonics. Also, I just surveying for such journals, which are now we know that there are many problems to publish your good results in good journals here because of some general problems. And yeah, if you have good works, these Chinese journals are very open for submission for international teams. So please, if you have any good ideas, you can contact me, and then I can recommend you which journal you can select. And yeah, if you have any other questions, so you can feel free to contact me. And here I would like to thank for your kind attention. Thank you.
Thank you, Sergey. The talk is open for questions, please. Who is ready?
Service.
Thank you very much for the very comprehensive talk. You told that thermoconductivity is very slow in perovskite. What's bad with phonons there?
Yeah, so phonons, they have very low frequencies. Because of lead, cesium, and in this case, so generally, and lattice also very soft. So we have very soft lattice. Young models is very low. So the complex of these features just give us very low thermal conductivity. So generally, this is the properties of lattice. Yeah.
Thank you very much.
Next question, please.
Thank you very much, Sergey, for this interesting talk. I would like to ask you, what do you think would happen if you focus femtosecond laser beam inside the bulk, not on the surface, but in the bulk? Do you suggest that do you produce some cavities or what?
Yeah, so in this case, actually we never studied such cavities formation in our perovskite. But yeah, obviously there should be some cavities. But I should say that there is a now new big direction when people prepare some glasses like ceramic, yeah. So where with composition, such a composition where they have all elements for perovskites just to be formed. So let's say they're transparent initially, but then once you focus and initiate some optical heating, you start to crystallize, you start to nucleize these perovskite nanocrystals. And there were many works starting from 2020, 21st, in China especially. So they produce many nice papers where show that different, like optical data recording inside such glass with containing perovskite precursors. So I think now this is one of the most rapidly developing field in this direction. But as for cavities, yeah, good question. So I haven't seen any interesting works about this.
How long it take time? How long to form the perovskite nanocrystal in the bulk? How many pulses needed?
Yeah, so in principle, we also, with Professor Nikanorov at ITMO, so they also gave us such glasses. And typically it's just, yeah, after several pulses, there are already some nanocrystals. Yeah.
Thank you.
More questions, please. We still have some time for questions, please. No more questions? Then I have to perform this.
Thank you very much. Yeah, thank you.
Now it's time for a presentation of our sponsor. I invite Anna Tsygankova. Is it here? Please. She will tell us about the products of the firm Научно-производственная корпорация.
Раз. Good morning, everyone. My name is Anna Tsygantsova, but it's but it's usual mistake. I will tell you from the part of industry. And first of all, I wanted to ask a question to you. Who in this hall associate yourself rather with industry and not with science? Except me. Two people from industry, others from science. Okay. Well, we work in the field of development and manufacturing of serial laser and not only laser systems for material processing for more than 25 years. And we are located here in Russia. And the main focus of our business is serial laser systems, but lots of works we do with different university, and there are lots of research and development at our part. Why is that so? Because all of our customers are such plants, such manufacturers, and their demand is always high-end systems. And the main focus, the key of our business is high-end systems where we implement the latest research, the latest investigations in science. That is why we don't live without science, and we prefer to give special tasks to science and research. I wanted to talk a little about tendencies, about trends, about complex questions, which gives the situation around us. And if we look at the laser equipment applications in 10 years, we will see that как включить? А какой кнопкой включается диод? Не так. Он очень тусклый, его не видно. So, without diode. The gray part is applications in electronics and microelectronics. And we see how dramatically it growed between in 10 years. And what does it mean? It means that all the systems and all the solutions which were made 10 or 20 years ago doesn't suit us anymore in the industry. And it also means that we have that the shortage of specialists is also very dramatical because, well, there is no such amount of people, such amount of specialists, and it gives us more challenges. What is needed in the industry at this moment? And we here talk not only about lasers and optics, we also, and mainly, we talk about systems as a whole. It's, of course, automatization and robotization. It's different things connected with Internet of Things and connectivity, integration of artificial intelligence, and so on and so on and so on. Why? Because industry always needs to solve the same problems. It's serial production, it's stability, it's the problems with shortage of specialists and so on. And all of these things gives answers, and it demands from systems different models, different units, which must be integrated here. For example, this is one of our platforms for microelectronics, for micromachining in microelectronics, and there are different systems which should be integrated to provide the final result. Stable, controlled, and what the usual plant needs. It's different kinds of power measuring systems, rangefinders, thermal scan, to grow the stability, the accuracy, and other different things which we need when we talk about serial production. And to provide this, we develop and serially produce different systems, because there is not only, well, computer and software here. There is also platform kinematic systems with high accuracy, which is also can be used for scientific instrument making for universities, because it was developed for laser and measuring system integration for, well, different goals. Other thing is specialized software, which is needed to provide the stability and the high quality results, because we can have fantastic laser system which gives us very good results, but without machine vision we cannot do anything. This is also different software models which we develop and which are integrated in our systems. And this, for example, is specialized software for temperature control, which is needed in the area of micromachining always. And here is... запустите, пожалуйста, видео. Here is an example of linking and positioning program model, which is used in microelectronics to link objects to holes, slots, pinholes, joints, crosshairs, and anything others, because we also need to solve the problem not to manufacture one part, we need to manufacture serial parts. And it's also the problem, and it's also the question and the field for development. This is one of the most demanded systems we produce. It integrates different laser types, because we hear here about femtosecond lasers, about picosecond lasers, about different, about green, ultraviolet, and so on and so on and so on. So the system should provide the possibility to integrate different types of lasers, different types of optics, and so on. And our systems, our platforms allows to do that. And here are the most demanded application at the moment, like plate separation, holes perforation, debonding, structuring, and these are most demanded in Russian industry at the moment. And there is another system which was suited to manufacture of thin film microstructures, and it also can implement different laser types, different optics, microscopic optics, and so on, and gives us positioning accuracy up to 3 microns. And all of them can be used in serial production and as a scientific research instrument. Here are some examples of applications which were developed based on these systems, and it's as we need it. Silicium carbide. I'm used to to give them names in Russian, so it's a little bit difficult. And it's a process like cutting, ablation, and we discussed the structure inside the material just a few minutes. And there are examples here when we need this process. This is ablation of как кремний будет на английском? Я, к сожалению, забыла. Silicon. This is also silicon, and I want to stress that these examples, in fact, are not what the industry needs. They are a little bit lower than they need. And here I want to impress that this is a field to intensive work between science and industry, because because every plant which gives the final details, the final I don't know what, they need systems with technology. And up to this moment, these results were made by ourselves, but we hope that working together with science, with institutes, we will achieve more interesting results. So I think that's all. Thank you very much. If you have any questions.
Our questions, please.
Okay, I have one small question. Do you have any products for educational purposes? Maybe some, I don't know, some lasers and laser systems for studying or for universities? Or?
For universities, of course.
Okay, so
yes,
and how open you are for some collaboration and education? I mean, for students, for some. Maybe some practices for students?
Of course.
Okay.
There are lots of practice at our plant. We are located in Leningrad, not in St. Petersburg, but yes, we are also open to this.
Okay, thank you.
More questions? So, after that, we stop. Thank you, Anna.
Thank you.
And the scientific program is over, but we have some announcements from the organizing committee.
Okay, thank you. I have actually two announcements. Okay, so the first announcement is related to our poster session. It is already ready for your discussions, and I hope that all the presenters will be there from 11 to 11:40, I think. And the second part of this session will be from 5:30, I guess, p.m. to 7. So all the presenters are recommended to be near their posters, and all the listeners are recommended to have a lot of questions during our poster sessions. We have also extra special competition this year, so all of you have special packs in your organizing packages. They include some stickers. So these stickers are for voting for the best poster. So you can vote for any poster up to 10 by just sticking these red marks to the special blank zone near the number of this poster. So then we count the number of these stickers and choose the best poster each day. Повторю на русском. У каждого есть красные стикеры, красные кружочки, которые можно вешать на постеры в специальное поле, которое находится рядом с названием, с номером постера. Если вам понравился этот доклад, вы можете приклеить туда наклеечку, и мы потом посчитаем наклеечки и выберем, собственно, лучший постер, который будет сегодня и который будет завтра. Победителей наградим уже на закрытии. Okay, and now we have one more announcement. This is announcement from Chief Editor of the Journal of Optical Technology, right? So Valery Viktorovich Korotaev would like to tell us about how to publish in his journal as the result of the conference. So please, let's welcome Valery Viktorovich.
Спасибо. По результатам прошлой конференции наш журнал выпустил хороший выпуск. По результатам вот этой конференции там были представлены лучшие материалы лучших докладов, это были лучшие статьи. И мы планируем в этом году тоже сделать такой выпуск. Я надеюсь, что он будет достаточно высокого научного уровня. Что нужно? Собственно, алгоритм очень простой. Можно просто в любом поисковике найти, набрать оптический журнал, и вас сразу же выведет на наш сайт. Сайт у нас новый, достаточно подробный. И там есть страничка «Структура статьи». Вот прошу внимательно отнестись к содержанию этой страницы, потому что все, что там как написано, понимать надо буквально. Вот просто буквально. Как написано, так и работаем. Ну, а журнал наш уже достаточно, если кто-то тут, может быть, из молодежи не знает, но журнал, которому уже более 90 лет, журнал, давно издающийся американским оптическим обществом, он переводится в Соединенных Штатах и издается версия. В результате мы входим в базы Web of Science и Scopus, ну, в белый список, список ВАК и так далее, и прочее, прочее, прочее. Вот, так что ждем хороших статей. Алгоритм очень простой. Присылаете на адрес нашего журнала свои материалы в соответствии с тем, как это написано на сайте. Но сделайте пометку в теме, укажите, что это статья в рамках конференции FLAMN. Ну, а дальше там уже разберемся. Дальше будет процедура рецензирования, ну и так далее, собственно. Ну, поскольку журнал научный, то, естественно, критерием отбора будет наличие научной новизны и практической значимости. У меня, наверное, все. Я готов ответить на ваши вопросы либо здесь, либо потом у входа где-нибудь тут рядом. Q3. Знаете, мы планируем вот этот выпуск сделать первым номером следующего года. Дело в том, что у нас портфель, я бы сказал, не то что наполнен, портфель переполнен, поэтому до конца года уже, в общем, все забито, но мы целевым порядком планируем первый номер. Но если у кого-то что-то очень горит, справки мы, конечно, выдадим, но если у кого-то что-то горит, так сказать, в рабочем порядке, можем еще немножко порешать чуть-чуть про 12 номер.
Извините, у меня есть вопрос. До когда есть время, чтобы публиковать вот это статьи? Дадим статьи дело публиковать. Вот это я здесь.
Чем быстрее вы пришлете ваши материалы, тем мы быстрее их обработаем.
Спасибо.
Ну, у нас совершенно четкая процедура рецензирования, поэтому тут еще немножко зависит от рецензентов. Потому что есть рецензенты, которые присылают рецензии на следующее утро, а есть рецензенты, выдающиеся ученые, которые пишут дольше.
Может быть, для моего понимания, FLAMN-2025 – это что такое для вас? Это просто конференция, и каждый пишет… Сейчас, минуточку. Обычно ведь, не верю, иногда, очень часто сам факт представления материалов здесь уже является одной рецензией. Это типично для вашего журнала или нет?
Вы знаете, у нас все-таки достаточно четкий отбор и есть совершенно четкая процедура.
Тогда
рецензирование, да, значит.
Тогда ваше преступление – это реклама посылать вам, вам статьи, нет? Потому что мы хотели бы все-таки как-то обозначить и позицию нашей конференции.
Ну, дело все в том, что поскольку здесь собрались практически все специалисты в данной области, то рецензенты в основном будут из числа участников конференции. Так что в этом нет ничего страшного. Более того,
спасибо.
Я вам скажу такую вещь. Для того, чтобы обеспечить качество журналов, у нас совершенно четко все статьи, которые прошли рецензирование, выкладываются на обсуждение всех членов редакционной коллегии в полном составе. Поэтому, ну, скажем так, где-то 1 из 20 статей в результате после рецензирования, тем не менее, возвращается на доработку. Именно по результатам, потому что у нас есть замечательные рецензенты, вот здесь вот члены нашей редколлегии присутствуют, Николай Валентинович. Вот. Тигран Арменакович, люди, которые в значительной степени, ну и другие наши коллеги, которые обеспечивают качество публикуемых материалов. Оптический журнал издается на русском языке, Journal of Optical Technology издается на английском языке. Нет, американцы переводят. Они переводят, да. Да, значит, эта традиция уже с 1966 года, идентичные материалы абсолютно. То есть журнал идет в один в один. Единственное, что мне осталось, вот журнал. Это выпуск как раз по итогам прошлой конференции. Вот он выглядит, вот такой вот журнал. Вот так это все. Ну, если все, я готов уже ответить на вопросы в частном порядке. Спасибо.
Давайте еще раз поприветствуем. В целом мы готовы закрыть нашу секцию. Я благодарю наших уважаемых председателей секции Тигран Арменакович, Сергей. Большое спасибо нашим пленарным докладчикам, собственно, которые тоже здесь присутствуют, Алексей и Сергей. И я вас приглашаю на кофе-брейк, который будет совмещен с постерной сессией. Спасибо.